All right. Yeah. So thank you for the introduction, Zihan. And yeah, I'm gonna spend a while telling you about some parts of this result, and it's joint work with all my wonderful collaborators up there. And please ask a lot of questions along the way. I don't have like I have written something like 25 pages of notes that I'll start to put out on the blackboard, but I'm not thinking we'll get through all of them, okay? So I would rather that you make sure for yourself that you understood some part, okay? Also, yesterday when I was taking the Uber back, the Uber driver told me, oh, you remind me of when I was in Denmark, when I told him I was Danish. And he said, where people are cold, disinterested, and unfriendly. and I was, oh, thank you so much, stunned into silence, obviously. So then that sort of fulfilled the prophecy. Today I won't be silent, and neither should you. Okay. So what is maximum flow and minimum cost flow? We're going to start with an example, apples on trains. And here is a train network from the USSR, which is where people first started to think hard about flow problems. This clicker is maybe a little... Okay. So let's imagine that some cities have a surplus of apples and others a deficit, and we're trying to answer the question of how can we cheaply route apples from the cities that have a surplus to the cities with a deficit. And the simple model we'll use is we'll represent a city with a vertex in a graph and a train route with a directed edge in the graph. And if you want to allow the train to go in both directions, you can put in both directed edges. The routes, they're directed, as we said, and they have a cost. You can think of fuel spent per ton of apples that you're sending, and a capacity, say, tons of apples per day that you can send. There won't be a time component to this, so we can think about just trying to route what we can in a day. So for example, here, we have a cost of 1 and a capacity of 2, and then we can send 2 units of flow on that edge respecting the direction. And this then will cost us 2 times 1, and the capacity is being respected, so we're not sending more than 2 units, so that's allowed. So here's a slightly bigger example. We've got a surplus of 2 apples at the top and a deficit of 2 at the bottom, and then we're routing here 2 units along one of these routes, okay? And what's the total cost? It's 2 times 2 on the first edge plus 2 times 1 on the second edge for a total of 6. All right? Is that optimal? No. Can somebody tell me why? Yeah? There's a cheaper route, absolutely. So it's not optimal. It's cheaper to send flow the other way. So here is a different solution, which is in fact optimal. Now we're sending 1 unit down the cheaper route. That's as much as we're allowed to by the capacities, okay? And the new cost is less. It's 5. All right? Okay. So, but how? This is kind of pretty clearly an optimal solution, okay? Like I send as much as I could on the cheapest route, and then I sent the rest on the less cheap route. But more generally, how can we think about improving our solution? Oh, and maybe before we go there, so this is what min cost flow is, right? So minimum cost flow is that you have capacities in a network, you try to route flow that satisfies your demand, so like where the stuff comes in, where it goes out, and then you try to minimize a linear cost function. Generally speaking, you also allow negative costs, and that's also fine for the algorithms we'll see. Okay, so more generally, how can we notice that we don't have an optimal solution, right? For this, we'll build a new network and try to use that new network to discover ways to improve our solution. So here, I started with some flow on an edge. There was a flow of 1.75, a cost of 1, and a capacity of 2. Now I'm going to build a new network with no flow on it, in which I'll try to discover ways to improve my solution. Okay? And the way I do that is that I first make an edge corresponding to the original edge, but I reduce its capacity so that it only has like the leftover capacity, right? And the cost stays the same as before. Then I add, so this is the 0.25. This corresponds to the fact that we still, in the original graph, have forward capacity on the edge of 0.25. Okay? Then I have an edge going backwards with capacity equal to the flow on the edge, corresponding to the fact that that's how much flow I can take away from this edge. Okay? And this has a negative cost corresponding to the fact that if we reduce flow on that original edge, then we reduce the cost of the solution. So this is called the residual network with respect to this flow. Okay, and I think you've probably all seen the residual network in the context of max flow. The only thing we added here is that there's a negative cost going backwards. Okay, so now let's look at our example from before. So we had our bad solution here, which was not optimal. Now we construct the residual network. And here we don't have forward capacity on the edges on the top anymore, because they just have 0 capacity left. So I just didn't draw those. Then we have backwards edges with a capacity of 2, corresponding to the fact that we have 2 units that we can take away. Okay. Now notice that there is a cycle here in this network. I painted that in purple, which has the property that when I add to my old solution that cycle of flow, then I get this better flow, right? The cost in this residual network of that circulation or cycle is -1, and it's feasible. So this circulation or cycle, it respects all of the capacities in the residual network. And by construction, this means that if we add the circulation to our original solution, we get another feasible solution. That's sort of how we set up the capacities in the residual network. And the cost of this circulation corresponds exactly to the change in the cost that we'll get in our updated solution, right? So we reduce the cost by -1. Okay. And this is going to be basically how we'll improve our solution. We'll construct a residual network, and then we'll look for cycles. So we start off with some bad solution, then we keep finding cycles that improve our solution. This goes all the way back to a guy called Tolstoy, who realized that you could get an algorithm this way in the 30s. Okay. It's not the author. Okay, so this is our program, min-cost flow. We have a flow vector on the edges that we're trying to minimize over. We minimize a linear cost function of the edges, so just flow times a fixed cost vector. And then we have a constraint on all of the edges that the flow should respect the direction, that's saying that it's positive, and it should be less than the capacity. And then we also have a constraint that, like, for every vertex, as much flow should come in as go out. And maybe you also have a source and a sink where you have a different constraint, right? That like some stuff is coming in there, appears there. But you're fixing the amount of flow coming into to equal the amount going out of every vertex. That's the last constraint. Okay, so as a little bit of linear algebra notation, we can write it in this way. Okay, so here I'm writing inequalities between all of the edges like this, which is sort of vector notation. And I'm writing this linear constraint that the net flow is 0 on every vertex with this matrix B, okay? It doesn't really matter what B is, it just is the matrix that corresponds to the linear equations that we had a second ago, right? Okay, we can solve this in m to the 1 plus little o 1 time. That's the result. This assumes that the capacities in the network and the costs are polynomially bounded. Okay? Otherwise, we have a logarithmic dependence on those. Now, we can actually generalize this quite a lot, so we can also put in a convex cost function on the edges, and any convex cost function is fine. There's some kind of technical condition. I don't know how to construct a function that doesn't satisfy it. So basically, any sane cost function on the individual edges is fine. Okay, so we get a lot of applications. We heard, about the fact that there are many yesterday. Yeah.
Is that new, that you can have many cost functions, or is previous work usually also fine with any cost function?
So the question was, is previous work also usually for any cost function? And the answer is it depends. So a lot of the fancy algorithms are restricted to linear costs or no costs, only doing the feasibility problem.
By fancy, you mean interior point method stuff? Or?
By fancy algorithms, I mean, for example, the almost linear time algorithm for undirected max flow, or the only algorithms that non-trivially beat standard interior point methods. Okay, so there's a lot of applications, and then you also get some more applications, including things that statisticians like entropically regularized optimal transport when you switch to this more general convex framework. Okay, so let's do a tiny bit of flow algorithm history. Okay, so we have m edges and n vertices. I'm going to try and use the same notation as Thatcher-Pohl did yesterday for our graphs. And in the beginning of research on flow algorithms, there was a long era of purely combinatorial algorithms. Okay, and this starts with Ford Fulkerson in terms of actually getting a running time analysis. Otherwise, it starts with this guy Tolstoy in the USSR in the 30s. But Ford Fulkerson showed that you can solve max flow with maximum capacity U on any edge in m squared U time, essentially. And then Sleater and Tarjan. So here I think I'm maybe even giving the time for min cost flow. They got down to mn. Goldberg-Rao got m power 1.5 for max flow. Okay, and this was the culmination, really, of this combinatorial era. Now, these are combinatorial outer loops that construct the residual network, and then you make progress by finding flow circulations, or in max flow, flow paths in the network to then send flow along. Okay, so that's you construct this very combinatorial object, that's the residual network, then you look for a path in the residual network, and then you send flow along it. Then we got a very different era of algorithms, sort of continuous era, I'll call it. This started arguably with Deitch and Spielman in 2008. And they made in retrospect, very simple observation. So maximum flow is a linear program, and minimum cost flow is a linear program. In a very different community, people had developed algorithms for solving linear programs that essentially they solve a linear equation in each iteration, and they do that in the case of max flow for square root m iterations. Okay, so you're just doing time for a linear equation times square root m iterations, and then you've got your maximum flow or your min cost flow. And then what Deitch and Spielman noticed is that when you're solving a linear program, you can set up these algorithms, they're called interior point methods, such that those linear equations have a very special structure. They're then called something called Laplacian linear equations. And these Laplacian linear equations we can solve in almost linear or nearly linear time, so O tilde m. Okay? And so now you kind of directly, by just using these solvers, you get this running time of m power 1.5. But this is just by looking at a standard interior point method a standard algorithm for solving linear programs coming from a different community and saying that actually once you realize that we have a good linear equation solver for this special linear equation, then you match 50 years of combinatorial algorithms, right? And the most sophisticated ones we have. And also, Deutsch-Spielmann works for min-cost flow, whereas Goldberg-Rao is restricted to max flow, where you don't have costs. And then this ignited a lot of interest. So we got a lot of progress. So Madry went below the standard interior point method time of m power 1.5. So he gave like an interior point method that uses fewer iterations. But this U here should be the max capacity of any edge. And so it only really works well when U is small. So like in a unit capacity network, basically. Okay. But this really hinted to us all that like m power 1.5 is not the end of the story. And then there was kind of a lot of progress since on various special cases. Dense graphs, for example, were solved by this Brand et al. In nearly linear time, right? So this running time of m to the m plus n power 1.5 in a dense graph that's nearly linear. Okay. All of these algorithms, they use this thing called interior point methods, which we'll see in a moment. It's a continuous algorithm that asks you to improve your solution by solving some update problem, which is then corresponds to a linear equation. And so because it's doing continuous optimization, I'll call it a numerical or continuous outer algorithm. And then the inner problem that's being solved here is a linear equation. And this corresponds actually to doing an electrical flow in the graph. So we haven't seen what are electrical flows. So if I minimize sum over edges in a graph and I have some resistance on every edge, and then I have a flow on the edges, and then I have a constraint that I'm routing my demand, so BF equals some demand. This was the net flow constraint, so saying that the flow routes this demand. This is called electrical flow. It can be solved by solving a single linear equation, a Laplacian linear equation. And it's not a combinatorial object at all. Okay? It's sort of a smooth object that sends a little bit of flow everywhere in the graph.
Sorry, you can't return entry. What did you write above the exit square?
This thing?
No.
So this says resistance times flow squared. Sorry, this was just some weight on the edge, which I'll call resistance, because it behaves like resistance in physics. Okay. So this era, by the way, sort of all these algorithms, they can sort of be broken down into two kinds of improvements. There are improvements that make the outer loop take a little fewer iterations. So if you've heard of accelerated gradient descent, how many people have? So at least half, and maybe the other half are just lazy. So this, morally speaking, is a bit like realizing that you can do accelerated gradient descent to interior point methods. Okay, so you can get like a slightly better iteration count. And then these later algorithms, they're instead saying, actually, we can take a data structure and realize that this data structure can help us compute all of our many electrical flows. So we're not just solving one linear equation, we're solving many, many linear equations. And these are quite closely related. And so because of that, you can build a data structure that helps you get out the solution to many electrical flows more cheaply than just solving each of them independently. Okay. This is very hard work, however. So you can see that in sparse graphs, so when m is close to n, this m plus n power 1.5 is not really giving any improvement. And all of our smartest people, or at least a good chunk of them, working very hard here on using data structures to improve sparse graphs got us from m power 1.5 that to m power 1.48. Okay, so it's really hard to build data structures to accelerate this computation of many electrical flows. So we skipped to the end in some sense. We got m power 1 plus little o 1. We're using a numerical method as the outer loop, but where the it's an interior point method again, and we'll see what that means in a moment. But in the past, these interior point methods made progress by solving a linear equation, which is an L2 problem in each iteration. We're going to make progress by solving an L1 problem. Okay, we'll see what that means in a little bit. This is much worse. Okay? So these L1 problems, they are not nearly as well suited for making progress. And that's why this interior point method needs a nearly linear number of iterations, so m power 1 plus little o 1 iterations, whereas the old interior point methods only needed square root m iterations. So we need much more iterations because we're taking worse updates. But these updates now have a much more combinatorial structure. They turn out to always be single cycles. So before, every update was a flow that touched the whole graph. Now an update is a single cycle in the graph that you route some flow along. So it goes back to looking a lot more like this algorithm of Tolstoy in the 30s that we saw in the beginning. Okay. Then we'll build a data structure that will get us each of those cycles, so each iteration of the interior point method, in amortized m to the little o 1 time. And that's then going to be the whole algorithm. Yeah?
So for the L2 norm that so basically these flows that you're writing, minimizing L2 norm became solving some system of equations. L1 norm was mean cost flow. I guess L infinity norm will be some water like a semantic or something. But what happens for other norms? Like what is so special that L2 can just solve linear equations?
So the question was, what's so special about L2? Why can it be solved in few iterations? So I spent like 3 years really working full-time on the question of what happens for other values of p. And that was actually how we came up with this algorithm. So we were trying to solve like 100 norm flows. And it turns out that like when you're thinking about 100 norm flows, then you get to use some of the same tricks that you get to use for L2 norm flows. So really sort of, you still need like most of this machinery. But there is one sense in which like all flows except infinity and 1 have a lot in common. And that is like when you develop the right perspective, a kind of smoothness to the objective. It just took us a very long time to think in the right way about that smoothness. Does that help a little?
But, you know, like at infinity it is easy, then you're saying it becomes a bit hard, then at L2 it is easy.
No, actually that's not what I mean. What I mean is just that, so for a very long time, the situation was that we had L2, so 2 norm flows were easy, and then just everything else was the same and it was hard. Then at some point we realized that for large p, so like, but not infinity, in the unit capacity case, this was 2019, we could go down to easy again. Like this is, say, almost linear time, and this is 1.5. And then there was another work that said that actually there is kind of a smooth behavior in iteration count. So you can get like something that's like an interior point method, but which will converge very fast with very few L2 solves when p is close to 2. And then sort of this like weird region here where things were easy for a while was only for unit capacities. And this algorithm then came out of first trying to do all p except 1 and infinity in this time. And this is coming from the fact that like once you have the right perspective, all objectives except for infinity and 1 have a certain smoothness to them, which you can then use in your continuous optimization in some way. So let's talk about interior point methods. So we're going to use an interior point method for solving a flow linear program. And so let's forget about like the constraints that say, how much flow is going into and out of various edges. Let's just think about the inequality constraints. These are the hardest ones, okay? So here I've got two flow variables, f1 and f2, and I've got some constraints on them saying that f1 should be greater than or equal to 0 and less than 4. Confusingly, I guess I put f1 along the y-axis. And f2 should be greater than or equal to 0 and less than 6. And then I've got some objective here pointing in some direction, okay? And then I need to minimize over that objective, and in this like toy program, that orange dot is the solution. Okay, and I think I mislabeled something, but you get the idea. Okay, so this is a linear program, and people, not really in theoretical computer science, but in optimization research, have thought a lot about getting polynomial time algorithms for linear programming. This started with the ellipsoid method. And then we got Karmaker developed the first what's called interior point method, or rather he analyzed an interior point method for the first time in a reasonable way. So the practitioners were already doing it. And then Renegard developed a second later interior point method that's also kind of very important. So I just put it on the slide. But we're actually going to build on the first interior point method due to Karmaker. Okay, so what are these interior point methods for solving a linear program? They want to turn the problem into continuous optimization. So they're going to say, we want to guarantee that f is greater than or equal to 0. That's like a hard constraint. We're going to turn it into a soft constraint by modeling it with this barrier function b of f, which has the property that as f approaches 0, it goes to infinity. So it's some function that blows up to infinity if we violate the constraint. Okay. Now, we'll create a potential function for this linear program. Okay. And this potential function applied to our flow. So first it's going to have a term, let's forget about it. It tells us we need to improve the objective value, right? So there was some cost function, we need to push that down. Ignore that for now. The second one, I think, is the more important part to understand first. So this is a sum over our edges, and then we put in a barrier for each of the constraints that we need to enforce on that edge, right? So this is saying we have a barrier on the flow. That means if we get too close to 0, the cost will blow up. And we have a barrier on capacity minus flow. That'll blow to infinity if we start to violate the capacity. Okay. And you can think about we're putting in terms of we're watching the plane here from above, we're putting in gradients that are pushing us away from the constraints. Those are my green arrows there. But we're still, like the light green ones, we're still trying to move as far as we can in the direction of that green arrow, right? That should be our goal, this objective arrow, the darker one. So we need one term that says that you get a bonus for making that objective better. And we do that with a cost, the cost of the objective minus the optimum cost. Assume we guessed it. We'll have to binary search for it. And then that barrier is put in with a minus sign. So that actually sends us to minus infinity. Okay? So this is giving you a bonus if you do get the cost close to opt. Okay? And here, yeah?
I have a question. Is the B here the same as this constraint metric? Or no, you had the letter capital B for constraint metric?
Sorry. That is totally my fault. So I put in a B for the constraint matrix. Here I'm using B for barrier. Absolutely no relationship, okay? Thank you. Good. Very good question. Okay, so here I did an actual plot of some barrier functions in Mathematica. So these are constant value curves with different colors for different values. And you can see we're being pushed away from the boundary everywhere, except that if we manage to go and actually make the objective small, we still get minus infinity. Okay?
On the boundary, like on the objective point,
Yeah.
what's the value of the thing? Does it become infinity or minus infinity, or what happens?
There's a question about like what does the function do? So the function is set up, maybe I should have added like a minus 10m instead of minus m. The function is set up so it's approaching minus infinity as we approach the optimal point. Yeah? Oh, m is the number of edges.
Oh, okay.
Okay, so I'm scaling up this barrier function, the one that rewards us for improving the objective, in order to say that like if you actually manage to improve the objective, it has to overwhelm the fact that you need to get close to the violating the constraints in that direction. Yeah?
You're doing exact flow, right? And I know in least for stuff you round at the end. Is that always the case that you need to round from an approximate flow to an exact flow?
So there was a question of, we're doing exact flow, do we always need to round at the end? And the answer is yes. Like just, at least that's the only way I know how to really say that you got there. In particular, the exact solution will tightly satisfy some constraints. And that would blow us to infinity here. So like at the end, we're kind of extremely close to the answer, and then we can just trivially round it, it turns out, to the right answer. Yep. Okay, so now how are we going to use this barrier function or this potential? So we're going to get some bad starting point, okay, f0, but which is feasible. Sorry, question?
Can you please comment on the previous slide?
Yeah.
I'm a little confused on how the optimal values for f1 and f2 are 0 and 6 respectively. Because if you want to minimize say, like negative 6 f1 plus f2, would you just set f1 equals 4 and f2 equals 0?
So here, let's see, it's very possible that I put some signs wrong. Like, I think we're just minimizing, so the question was, didn't you get the signs wrong? Is that a fair summary?
Like, shouldn't it be, instead of 0, 6, shouldn't it be negative 4, 0? If you want to.
Oh, yeah. So, probably. Let's see.
I think if you switch F1 F2, then
I think I switched like F1 and F2 in some place, and then it would be this. Yeah. Okay. Sorry about that. Like, I guess like every sign has like a 50% probability of being correct. Sorry. Okay. So we start with some solution, a bad one. So how do we even make sure that there is a feasible bad solution? Okay. If we just have a single source and a single sink, this is very easy. You just put, so we have like our graph, you just put in one special edge that has plenty of capacity, and then you route all the flow on the special edge, and then you make it very expensive. Now you have a bad solution that you can start with. So we can always get like, modify the graph a little bit so we can start with a bad initial solution that's feasible. Okay? So we have a bad initial solution that's feasible, and now we need to improve it. So we want to take some step, an adjustment delta, that we add, and then we get our new flow, which is then better with respect to this potential. And we just keep doing that many times. Okay, but how? Right, so what's going to guide the choice of the update? So in continuous optimization, there's, roughly speaking, only one algorithm. So the answer is always do a Taylor series expansion. And now you have like an approximation of your function that's simpler, and now you try to minimize that one. Okay? So here, I did a second order Taylor series expansion of my function. Okay? This gave me an upper bound on the function. And now this upper bound has like a constant term, a linear term in delta, and a quadratic term in delta. Okay? And hopefully it's simpler. So like, do we all know sort of like why is it easy to upper bound a convex function with a quadratic function? Or not necessarily even a convex function? Like what is the, can somebody sort of describe to me what are the steps that I need to take to upper bound a function? Not necessarily. Sorry, I'm not saying you should know, I'm just asking.
You could ask with some kind of like Lagrangian values you have about.
Lagrangians, and yeah, I think that's usually a little bit more heavy duty than what we're looking for. I think all I'm trying to say is that I have my function, this phi. Let's just think about it in one dimension, okay? Now, if I take a Taylor series approximation here to first order, then I have like a linear function that approximates my function. And if it's convex, it'll sit below, okay? Then I can look at its second derivatives. And usually if it's a function that's growing fast, the second derivatives will create another function, if I add them in, that locally kind of agrees, but globally it sits below a little bit. Okay? Now all I have to do is scale up the second order term a little bit. Okay, so this is like the function plus, so at the initial point, plus the gradient of the function times my variable, plus the second order term, which is a quadratic, and then scaled by, say, a factor 2. Okay, so if I scale up the quadratic locally, it sort of curves up a little bit above my actual function. And now I have an upper bound. This is a quadratic function, so it can't be an upper bound everywhere, because the quadratic is not going up to infinity, but the actual function is going to infinity. So the next question is like, what kind of region is it an upper bound in? Okay? And basically, so let's multiply by 4 instead of 2, give us a bit more slack. Now you start with some second order term which is coming from the Hessian matrix of the function. That's just the second derivatives of the function. And now you just have to stay inside a ball where the Hessian has not, the second derivative has not increased by more than a factor 2. Okay? So if the thing has increased by a factor 2, then 4 times the original thing is still like 2 times the current thing. And so I end up with an upper bound. So in a box where the second derivatives have not changed by more than a factor 2, I can get a very simple upper bound. And that's the kind of box we'll try to stay inside. So this thing is an upper bound, but only locally. And now let's talk a little bit about this g. That's just going to be the gradient of the function. Okay? And this L should be the second derivatives, but then multiplied by a little bit. Now this is just a good approximation of those second derivatives. Okay? Because the barrier function on a single edge looks like this. Minus log FE.
Rasmus, would you write it white, please?
Write in white. Yep, sorry. Thank you. Good. Minus log FE plus minus log, so let's drop the plus, just write minus. U E minus FE, okay? When I take two derivatives of this, I get 1 over FE squared plus 1 over UE minus FE squared. And this is basically the max of these two, right? The sum is just at most 2 times the max and at least half the, and at least the max. And that I can also write as like the min of, like 1 over the min of these things. Okay? So we didn't say which barrier function. Yes, thank you. We're going to use log as the barrier function, this minus log. Okay? So why minus log? Well, it fits the picture. I think that's all we'll say about it now, right? So log looks like this, and so minus log looks like this. So it at least satisfies the thing about blowing up to infinity. Okay? Maybe the other thing to realize about it is that it has these very nice derivatives. Okay? So now here I'm writing L. It doesn't have the square. That's then because we're making a diagonal matrix that we're multiplying the update with that gives us LE delta E. And then we're taking the 2 norm of that vector. So I'm getting sum over E, LE delta E squared. And this LE squared, if I pulled it out, so LE squared delta E squared, that's the second derivative, up to constant factors. Okay. Now, suppose, so I wrote there symmetrized residual capacity. I think I should have skipped that until later. Question? Yeah?
Yeah, so this is only the second derivatives of the part that isn't related to the cost, or to the cost function, right?
Oh, yeah. So I dropped the second derivatives related to the cost function. Is there a reason? Great question. There is actually a reason. That's like a little Easter egg for those who notice. Otherwise, I was just going to pretend nothing happened. So generally speaking, if I'm trying to make an upper bound to my function. When I use a linear function to approximate a convex function, I get a lower bound. Okay? But on the objective term, I was using a concave function, so it looked like this. And when I plug in a linear function, I get an upper bound globally. So I don't need a second order term to make sure that I have an upper bound on this part. Yeah, good, very good question. Yeah. Okay, so I wrote symmetrized residual capacity. I think we'll get back to what that means. Okay, it's just a way to think about what these lengths are doing. Unless you want me to say it now. Undecided. Okay, I should have a plan, right? Okay, so now, of course, I left out the linear constraints, right? But we do have linear constraints. So I want my initial solution, F0, to route my demands, which can be written as B, now meaning this routing matrix, equals my demands. And I want my updated solution, F0 plus delta, to route my demands. So it had better be the case that B delta equals 0. Okay? This corresponds exactly to the fact that we were always sending circulations around to adjust our solution, because we started with a solution that routed the demands, and we didn't want to mess with that. So we have to only make adjustments that don't change how much we're routing. Okay, so we need that constraint. And then we're going to minimize this objective, this upper bound. If we make progress on the upper bound, then clearly we also made progress on the real function. Question? Yeah?
Yes, just to clarify, this is the constraint matrix, this is not the barrier function B?
This is the constraint matrix. Okay, let's live introduce new notation. Okay, this is one of my grand schemes for graph algorithms. Is I'm going to fight to rename B partial. Okay, so let's do it here. You heard it here first. Why? Because then I can use B for barrier function. No, that was actually an accident. It's because mathematicians have already called this B for much longer than computer science, have called this B delta, or partial, for much longer than we have existed. And it avoids the problem that other people mix up B and B transpose. By which I mean everybody else defines B as what I call B transpose. So, okay, this should have been partial, like this linear matrix that enforces my routing constraints. Okay, so now let's think about this problem that we got. So if I'm looking for a good direction delta to minimize this quadratic function of delta subject to this linear constraint, then I can think about it actually as just minimizing the ratio between the linear term and the L2 term. Okay? So I want like a large negative inner product with the gradient relative to my L2 norm. These two problems do not have, like I could have also minimized this like linear plus quadratic. They do not have the same solution, but the solutions only differ by scaling. Okay, so this problem that I wrote here is just a problem of like which direction should you move in, but it's forgotten about like how big a step should you take. And then separately you can think about how big a step should you take. That's then easy to figure out. Okay, but this, so with the constraint that we're a circulation, so I wrote delta as circulation, that just means your net routing 0. This is electrical flow. Okay? So, like with everything that I told you, you can sit for a couple of hours and you can look up the right, like first couple of pages in my lecture notes about how do you upper bound a convex function, and then you can analyze interior point methods. Okay, it's not hard, it's just this and you'll be solving an electrical flow. Okay? So the electrical flows just come about naturally because we're doing an L2 approximation. Now, what is the picture here? So of course, like here I said electrical flow, it's somehow like an electrical circulation, but these two things are very similar. Yeah. Okay. So the picture is that this L2 thing is creating some kind of ellipsoid, okay? And then we're looking to move as far along the negative gradient as possible while staying inside that ellipsoid. Okay? That's like the trade-off that we're trying to do. So here, for example, I got this arrow to f plus delta. Okay. Now we're going to make like a deceptively simple change. We're going to upper bound our 2 norm by a 1 norm. Okay, and 1 norms are just larger than 2 norms, so that just still works. Okay, it's still an upper bound. So here we've upper bounded it by a 1 norm. Now we get that the update problem is this gradient ratio to a 1 norm. Okay? And the picture will be that we need to stay inside a 1 norm ball, which is this rhombus. Okay? This rhombus actually even fits like the coordinates here. So literally it would look like this. It has to be coordinate aligned. Okay? So we're just doing like a sum of L1 terms ratio to a linear function. And then we're minimizing over circulations this objective. Now, the picture is a little bit suggestive. It looks like the optimum will probably be on a corner of that L1 box, right? That turns out to be true in sort of once you have the right perspective on it. We're minimizing over circulations, but actually the optimum will always be realized by a single simple cycle. Okay? Should we try and prove that? Does anybody want to prove it for me?
Like you see again, like you get that.
So I have an objective problem up here of minimizing linear function relative to a one norm. Okay? I claim that the optimal solution to this problem is always achieved by a single cycle flow. Okay? So I know it's a circulation, but actually it's going to be a single cycle. Yeah?
It's multiple cycles, just the better one.
If it's multiple cycles, just take the better one. Yes, it almost has to be a proof like that, right? So what is the proof, roughly speaking? It's that I take an optimal flow, then I decompose it into cycles, okay? The sum of these cycles still has the same gradient as like it's just like a sum, right? But I can also decompose it in a way where the sum of the L1 norms add up to the L1 norm of the sum of the circulation, of the cycles, okay? So I can decompose my flow, so I have delta, into a collection of cycles, maybe let's call them Ci, such that L delta 1 norm is equal to the sum over I LCI 1 norm, okay? And I just do it by looking at like the flow directions in the graph, and then I just do a cycle decomposition. And you just have to check that you never actually need two flows to go in opposite directions on one edge when you cycle decompose a flow, and then that's it. And now when you have like a ratio of like sum over I G dot Ci divided by sum over I L Ci 1 norm, then one of the terms has to get that ratio as well. Okay, so when you have like a ratio of terms with, then there exists an I, so this is, now we're doing negative things, so this is less than the min over I Gi dot Ci divided by LCI. Okay, so there is a good cycle.
That's a slightly different statement than you just made, right? Now you say that there exists a good cycle, that's something else, and that the optimal solution is always a good cycle.
So this cycle is as good as the best solution. So like there is an optimal solution that is a cycle. There can also be optimal solutions that are not cycles. Yeah. Yeah.
So just to make sure I understand. So when we're talking about this problem here, it looks like it seems like we're kind of morally thinking of this as the minimum of G transpose delta over the L1 norm of L delta equals like something fixed.
Yeah.
And we just don't quite know what that is, but like that's sort of what we're thinking of it as.
Yeah. So we can like, I think the question was a bit like, why are you saying like it has to be inside a box because it's a ratio? And the answer is exactly that, like, I mean, getting the ratio right is the same as like assuming that the one norm is 1 and then minimizing the gradient term, for example. So I'm being a little bit like switching around between all these, not so carefully. Good, very good question.
Sorry, is it obvious that the solution doesn't change at different scales?
So separately, when I take the step, I'm going to figure out what's the right scaling. Okay, yeah. Thank you, good. Okay, so we just did my exercise. Okay. So now let's talk about these lengths being I call it now undirectified residual capacity. So what do I mean by that? I mean, these lengths have a funny connection to the residual network, okay? Because suppose that I have my original graph here. We remember the residual network with some flow on an edge, okay? Now I construct the residual network. I have my residual capacity of 0.25 going forward and my other capacity of 1.75 going backwards. Okay. And these two things, so 0.25 and 1.75, are exactly FE, that's 1.75, and UE minus FE, that's 0.25. Right, so that was the thing that we wrote down here was FE and UE minus FE. Okay. So you can think about that as two capacities, right? There's a forward capacity of 0.25 and a backwards capacity of 1.75. Let's take the smaller of those two capacities, and then that's 0.25. And then the length is just this LE, I'll now call the length, is just 1 over that smaller capacity. And so now I get, if I make the network undirectified, I'll put an undirected length of just 1 over the smaller of the two capacities on my edge and a directed cost that is the same as what I started with. So I still have cost plus 1 for going forwards and cost minus 1 for going backwards. Okay. So like that's how I view these lengths and the gradients. Okay. And now there's one thing that we for sure need from our updates, right? We want it to be the case that when we've made an update, we're still inside the feasible region, because otherwise we sort of moved out of where our barrier functions even make sense. Right? So we have to stay inside the feasible region. Now let's think about how that relates to our lengths. So we want that delta E divided by capacity is less than 1. If it's going forward, it should be divided by the forward capacity. If it's going backwards, it should be divided by the backwards capacity. And if I'm being stupid, I could just divide it by whichever one gives me the larger number. Okay? So delta E divided by the smaller of the two capacities is the same as delta E divided multiplied by the length. Okay? And so what I'm really, like a sufficient condition for being feasible when I add delta is that the maximum over all edges of LE delta E absolute value is less than 1. So the lengths can tell me about feasibility. Notice that that's the infinity norm of L delta. So we can make the infinity norm small by making the 1 norm small. Seems like a terrible idea, but we can do it. Now let's make it the 1 norm a little bit less than 1. Let's make it 0.1. Now for sure, when I add delta to my solution, I'm feasible again. Okay? But because the capacities, remember that like my second derivatives or my lengths, they're basically behaving like this, like UE minus FE and FE, right? Now, if I only change delta E on the order of a small fraction of FE or a small fraction of UE minus FE, whichever one is the smaller number, so I'm only changing it on the order of 0.1 times that, then I haven't changed either of these two numbers by more than a factor 1.1. Okay? So my lengths, if I keep this infinity norm below 0.1, then my lengths are not changing by more than a constant factor, which was precisely one of my goals for making sure that I was like in a meaningful box for my Taylor series expansion. So my Taylor series expansion was only useful when the Hessian, the second derivatives, has not changed much. And that's exactly what I'm getting by making sure that I move like with infinity norm less than 0.1. So then the lengths are not changing by more than a small constant factor. You can say like a similar thing about the gradient. It's a little bit more finicky, so let's not worry about it. So the gradients and the lengths are changing very little. If I keep the infinity norm below 1, now I'm even going to make the 1 norm small. Okay? So making the 1 norm small buys me something additional that's very strong. Okay? This infinity norm condition said that in every coordinate, I'm not changing the length much. The 1 norm condition will say that there's only a single coordinate at most that's changing significantly. Right? Because like the sum of all of these little changes is barely 0.1. So there can just only be a single coordinate that is changing significantly. Okay? So that is like a super powerful stability statement. On it, like once you kind of repeat this, there might be slowly other coordinates that got like a little adjustment, and it adds up over time to a significant adjustment. But on average, a step with small 1 norm can only change the length in 1 coordinate by a non-trivial amount. So not only do we have like a good Taylor series approximation locally, we also have that the problem is barely changing at all, roughly speaking.
Can you say again why L1 norm is a small? Why can't it split it between 2 coordinates, 10 coordinates?
It can absolutely split it between many. Suppose that I split it out between all of the coordinates. Then I'm getting like a multiplicative change of 1 over m. And if I can live with a multiplicative change of 0.1, now I'll just not update my length until it's received m changes, or 0.1 times m changes of this amount. So basically, like if you spread it out, then kind of you can keep letting the length stay the same for a very long time. Because like you only have a budget to significantly change 1. If you spread it out, then you'll need more steps to even change a single 1.
Yeah, but when you say change 1, I actually have budget to significantly change constant number. That's not a problem, but each time it's a constant.
Yeah, so we'll change a constant number of things in each round. Yeah. That.
Yeah, like it doesn't propagate. No, I change 2 and then 2.
No, it doesn't propagate. It's just basically you can keep looking for every edge that's like a bucket of how much change you've incurred in a round. And then you can just wait until that bucket had reached 0.1. And you cannot fill many buckets across many rounds, like only on the order of number of rounds. So to summarize, there is an L1 IPM, an IPM for min-cost flow, such that it takes an almost linear number of iterations, and each subproblem asks us to solve this min ratio cycle, this L1 norm, gradient to L1 norm ratio problem. It's going to actually suffice to solve this in each round very crudely. Okay? So suppose that I was aiming for a solution with 1 norm 1 and gradient in a product with the gradient of -1. If I got a solution with 1 norm 1,000 instead, I just scale my step down by 1,000. Okay? That's then going to cost me a little bit in iteration count because like I'll make less progress in each iteration, but that's it. So this algorithm is very, very robust to getting very crude solutions in each round. You just have to take a smaller step. That translates then into needing more steps. Okay? But this is a huge win because there's a lot of things that can do m to the little 1 approximate stuff that just does not, you cannot hope to do exactly, say like a spanner. Okay, so a spanner can here maybe introduce like a polylog error somewhere, and just doesn't matter.
What is the optimum value of the mean ratio cycle at each iteration? Is it like if I plug in the actual flow?
Excellent question. What is the optimal value of the min ratio? We'll get to it in a second, or at least to saying a little bit about it, but it's -1. It's on the exercise sheet. It's maybe the best answer. Yeah?
Is the only place that the sublinear factors coming in now in that we want to allow for ourselves to have like a sublinear approximation, or is there something else that requires the...
Very good question. So the question from Els was, are there coming sublinear factors from the IPM itself, or is it only from the approximation? It's actually only from the approximation. Okay, so at some point, one of you is going to open the paper and say, Rasmus, you lied about the barrier functions. And then I'll say, like, yes, but it was not important. Okay, so you can come to me later and you can say, Rasmus, you lied about the barrier functions, but I don't want to explain it here. They're just very, very slightly different than the log barrier, but it's a detail. Okay, then we got this super useful thing that because we're taking steps with small L1 norm, not only are the coordinates changing very little in a round, which was important for the Taylor series approximation, they're changing very little across all the rounds. So the total number of coordinate-wise changes to the gradients and the lengths is only on the order of m to the 1 plus little 1. This makes this problem an excellent candidate for data structures, okay? Because if we can have some kind of data structure that helps us maintain the solution, like get a solution to the problem, then we're only adjusting the problem in a constant number of coordinates on average between each round. So that's what we'll do. Okay, so we'll have a data structure that we can query, get a good cycle out, then route the cycle, then change the L1 ratio problem a little bit because the gradients and the lengths are changing a little bit, and that's it. Okay, then we ask the data structure again, but only a constant number of updates into the data structure on average per round. Okay. Now, it would be nice if we had a data structure for the min ratio problem in like a strong sense. Unfortunately, we end up not quite getting that. And this relates to this question, so don't try to parse the last bullet point yet. It relates to this question of an adaptive adversary versus an oblivious adversary. Oof. So can somebody tell me what's the difference between an adaptive adversary and an oblivious adversary? Yeah, okay, so it's cheating because many of you do research on it and some of you don't, but thank you, yeah.
Adaptive adversary can change his questions depending on the previous answer.
An adaptive adversary can change its questions depending on the previous answers. An oblivious adversary is an adversary for a sequence of problems that has already planned out all its questions in advance. Okay, and a lot of the time in data structures and other stuff, people study oblivious adversaries. So they imagine that the adversary has planned everything, all the queries, all the updates to the problem out in advance. Okay? That is horrifically false here, right? Because it's my updates that are changing the problem. So the data structure is part of a very kind of tight feedback loop, right? The data structure gets asked to provide a cycle, then we route along the cycle, then that changes the problem that the data structure has to solve. So we send some updates back to the data structure. So it's very much not an oblivious adversary. Now, we don't actually know yet how to solve this problem against an adaptive adversary. Okay, I'm trying to figure it out, but we don't know how. Instead, we managed to show that the adversary is not fully adaptive. Okay? And in what sense is the adversary not fully adaptive? We can prove that if you had taken delta equal to the difference between the true min-cost flow and our current solution, let's call it Fi, this at step I is a good min ratio direction. Okay? But now, let's say we found some good approximate direction. So now, like, this was a good update at step I. We didn't find exactly that, but we found some cycle that does roughly as well. Now we could be looking for the next update. And we know that there's a good direction that looks like the min cost flow minus the new current solution. Okay? But the new current solution is Fi plus the previous update that I made, which I'll call, say, delta tilde I. Just to remind you, it wasn't this exactly. It was a cycle that approximated this. Okay? So this is now a good direction. Okay? What is that? That is F star minus Fi minus delta tilde I. So it's the old delta I minus delta tilde I. So the good direction changed by this adjustment delta tilde I. I made that adjustment. That is a huge promise to have, because I know that there's a hidden good solution. It's hidden from me. I don't know what this direction, current solution versus F star is, but I know where it's changing. So we're going to use that very heavily in our data structure. We won't get into the technicalities of this, but basically I know that if I manage to get the first good solution, then I only update the good solution at places where I myself route flow. So then I'm going to ask the data structure, work a little bit harder on the edges that I made an adjustment to. So the data structure somehow gets a warning. These are the edges where the good solution has changed. Now, there's a whole thing called algorithms with advice. Also algorithms with prediction, and this is a slightly different thing, and algorithms that are learning augmented. And a lot of this is it's a hot topic right now, okay? So maybe, is anybody in the room studying something that sounds like that at the moment? Jan is, thank you, Jan. Okay, it's a hot topic, so you should ask Jan for and you can think about this as saying we built a data structure assuming that we get this very strong advice about where is the good hidden solution changing. Okay. Now you might be thinking, yeah, whatever. It's done. So why do I care about L1 IPMs, right? So here is, I think, a good reason to care about this L1 IPM. We've only used it once so far, right, for this flow problem. But actually, it's a general method for solving linear programs. So if you start with a general LP with m inequality constraints, we could write it like this. So like linear function dot our variable x, some inequality constraints ax less than b, and some linear constraints cx equals d. Now, if you run that through an L1 IPM, you get an update problem that looks like this. Okay? And the IPM statement is general. Okay? So it says that it suffices to solve an LP to solve this L1 update problem with kappa approximation O tilde poly kappa m times. And your lengths and your gradients, which now kind of might mean something very different in this linear program, are only going to receive a small number of changes. And you get this promise that the difference between like your current solution in the IPM and the optimal solution is a good update direction. So now if you can go look at your favorite linear program with an interesting combinatorial structure, you can ask yourself, is that L1 update something that I can build a non-trivial algorithm and data structure for? And you have this promise in the back that's very powerful. Yeah?
If your LP is the multi-commodity flow, what would be the problem that you need to solve?
Great question. So the question was, if your LP is multi-commodity flow, what would be the problem? It's on my open questions at the end whether you can use this for that. I won't say exactly what the problem is, just in the interest of time, we can talk offline. The issue, I think, that makes this kind of quite non-trivial, whether you would get anything, is that there are like cancellations that appear. So like in this L1 norm, there will be some terms that you're getting in L1 norm of like a difference of two flows. And the optimal directions might have like that difference of two flows getting a very small one norm. And so it's not easy there to say that there exist like good simple solutions. Jan has a paper. It's a long story, sorry. Jan will tell you about something that's morally a bit related to this later in the week. And this is very interesting. Okay. So let's just stand still for a minute, right? And we should go on break soon. But let me say that I have made an exercise out of this IPM, okay? And you really, like, if you know how to upper bound a convex function, you have all the tools, okay? So to actually analyze the whole thing to prove that this special direction is good, in the exercise, you'll first do it for just max flow, but then you can do it for everything afterwards if you feel like it. So the whole IPM is on the exercise sheet, and it's not a super hard exercise once you have the idea. Okay. I skipped in the exercise a little bit about how to think about the gradient, because we didn't talk about that. So you'll just handle the lengths and assume the gradient is fine. But it's worth doing. Any questions? Yeah?
So if I am interpreting this right, the kappa in this work is m to the little o of 1, and then that's the only place that is, I guess, the fact that is, I guess the approximation part that we haven't talked about yet for the min ratio cycle problem is where the almost linear instead of near linear.
Yeah, so the question was, like, kappa here is m to the little 1. That's correct. That's this almost linear factor. And that's the only place we're getting an m to the little 1. Now, inside the data structure that gets this m to the little 1 approximation, there's a lot of different parts that bottleneck it at that point. One of them being what Thatcher-Pohl talked about, a super nice question of expander routing. Okay, so let's go on break soon, but also let's start a little bit on the next part. So the second key ingredient is going to be to get a data structure for the min ratio cycle problem. Okay, and we're going to start with a warm-up we want to just solve a single min ratio problem approximately. Okay? So even that, it's not like completely obvious how to do that quickly. Okay. But the key thing is going to be, it's very simple. First, we sample what's called a low stretch spanning tree. I'll remind you what that is in a little bit if you don't know. And a spanning tree, of course, you all know. It's a tree that spans the graph, right? Now, if you think about an edge in the graph that's not in the tree, then that creates a cycle, right? So if I think about my graph, I have a spanning tree. I look at any edge that is not in the tree, then there is a cycle closed by the tree path between the endpoints and that edge. Okay? Let's call that a tree cycle. The best tree cycle will be a min ratio cycle, approximately. Okay. So let's talk a little bit about why that is. Oh, how much time does it take? You can sample a spanning tree like this in nearly linear time, and you can then check the quality of all the cycles in that same kind of time as well. Okay, so the definition of what's called a probabilistic low stretch tree is that you're sampling a random tree, a subtree of the graph, like a tree that consists of edges in the graph. And it has the property that in expectation, the length of the tree cycle is up to polylogs the length of the edge. Okay? So suppose this is our graph, and suppose we have some optimal hidden min ratio cycle here, and now we want to show that the tree stands a decent chance of finding a good tree cycle. Okay? So suppose, okay, there were some more edges in the graph. Here was my random tree. Let's think about the length of all of the tree cycles corresponding to edges in this hidden optimal circulation, which I drew also as a cycle here. So if I just, by linearity of expectation, if I just add up the length of those tree cycles and I take an expectation, I get O tilde the length of the original hidden cycle. So then by Markov's inequality, I'll get the same kind of bound with probability 1/2. Okay? Markov's inequality just says that like if you have a non-negative random variable with a certain expectation, it's at most twice that with probability 1/2. Okay? So there's probability 1/2 of getting this kind of bound. It's now worse by a factor 2, but it's still just O tilde 1. O tilde 1 means polylog, right? I'm using Thatcher-Pohl's conventions from yesterday. Okay. Now, what about the gradients of the tree cycles? I claim that if we add up the gradients of all of these tree cycles, like the sum of the gradients with the right orientations here, so the inner product, like the value of the gradient dot these tree cycle flows. Let's say it's 1 unit of flow on each cycle. Then we get the sum of the gradients on that cycle, optimal hidden cycle. Can somebody tell me why? They cancel out, exactly. So I'm using tree edges, but every tree path I'm using in one direction and in the opposite direction. So all of these terms, they cancel out when I add it all together. Okay. But now I'm done. Remember, we should have talked about the name. The ratio of a sum of terms where on the bottom things are positive, there's always like an extreme value realized by the ratio of one of the terms, right? Okay, up here, now I can say that if I divide the sum of gradients of tree cycles by the sum of lengths of tree cycles, then within polylog factors, I'm getting the min ratio value of the optimal solution. And so up to polylog factors, one of those cycles is good, because there has to be one of the terms that realizes the ratio. Okay, so that was the warm-up. Let's state the data structure, and then let's have a little break, right? So we have a randomized data structure. Now we're not doing the warm-up anymore, okay? And now I'm just going to say a little bit more about what the overall data structure for the min ratio problem is actually doing. Okay, it's going to maintain a collection of m to the little o1 low-stretch trees. And now you also need to handle updates to the problem, right? We can update these trees under getting changes to the gradients and the lengths so that in some sense they're still low stretch. And we can return an m to the little o1 approximate min ratio cycle. And we can route flow along such a cycle. Okay? So the data structure supports all these operations. And that's the goal. Okay, so let's go on break, and when is it that we start again? Like half an hour later, right? Thank you.
Yes, we are coming back in 30 minutes. So just a note, some of the tutorials from last day, the exercise has been already uploaded to the website.